Welcome to the Dive. I'm your host, and today we are plunging into a concept that sounds, well, like it was ripped straight from the pages of a sci-fi novel.
Hmm.
But it's increasingly making its way into our reality: reactionless propulsion.
Yeah, it really is something else.
Imagine, if you will, a world where movement doesn't require pushing off anything. No exhaust, no fuel burning, just pure, unadulterated force that seems to defy, well, the very laws of physics as we understand them.
It's a truly fascinating area, definitely, and one that absolutely challenges some of our most fundamental assumptions about motion.
Absolutely.
What we're going to be dissecting today is this incredibly detailed paper titled Reactionless Propulsion, authored by Randall Lee Mills and his team over at Brilliant Light Power.
Right.
And this document, it presents some pretty compelling experimental evidence for a phenomenon they actually call space drive.
Space drive. Okay.
Yeah, and they're claiming it generates force without an equal and opposite reaction, which, as you probably know, stands in pretty stark contrast to classical physics.
That's putting it mildly. Right. So our mission today is to really unpack the intricate details of their core experiments. We want to delve deeply into the underlying theory that attempts to explain this seemingly impossible feat. And then, crucially, look ahead to the revolutionary implications this could have for everything from, say, how we travel across cities to how we journey through deep space.
I think you change everything.
Get ready, because your perceptions of physics just might get a little shifted. So let's unpack this.
Indeed. To really grasp the truly revolutionary nature of this idea, we kind of need to start with what we all learned back in physics class, Newton's third law.
Ah, yes, good old Newton.
Right. It's a principle so fundamental it's practically hardwired into our understanding of the universe. For every action, there is an equal and opposite reaction.
Can't escape it, usually.
Exactly. This law is the absolute bedrock of how we understand all conventional propulsion. Think about a rocket.
Yeah.
It expels hot gases downwards. That's the action. And the rocket moves upwards. The equal and opposite reaction. It's the same for a jet engine, or even just you walking.
Right.
Right. You push out the ground pushes back, propelling you forward.
It's so ingrained in our everyday experience, isn't it? It feels almost intuitive.
Totally.
But what Mills and his team propose is nothing short of a special exception to this law. This is something Newton himself certainly didn't consider.
Not at all.
They suggest that when a free electron absorbs a photon, and this electron is already moving with a positive velocity relative to a very specific kind of inertial frame,
Okay, yeah.
it results in a reactionless force. That's a staggering claim. For our listeners who might recall Physics 101, linear momentum conservation is a bedrock principle, right?
Absolutely fundamental.
So to say it's not obeyed here, that's not just a tweak, it's a fundamental rewrite of a core concept. Can you underscore why that's such a radical departure?
It truly is. In classical physics, if an electron absorbs a photon, it gains energy, yes. But its momentum must be conserved through some kind of recoil somewhere.
Yeah.
Something has to push back.
Right, the equal and opposite.
Exactly.
Yeah.
But here, they're arguing that the linear momentum isn't conserved in the traditional sense between the electron and, say, another particle.
Okay.
Instead, the electron gains kinetic energy equal to half the photon energy, and the other half is related to this reactionless aspect. It challenges our very notion of what happens when energy is transferred at the quantum level.
Wow.
Yeah, the implications are profound because it suggests a way to generate force without the typical reciprocal kickback.
And what's fascinating here is their definition of the absolute space inertial frame of reference. That sounds grand.
It does, doesn't it?
They describe it as the frame corresponding to the creation of the electron at rest, where it has zero kinetic energy above its exact photon production energy. That's still a pretty abstract concept. Can you help us unpack what they mean by this absolute space inertial frame? It sounds like a fixed point in the universe, which is a pretty profound idea in itself.
Precisely. Instead of thinking of all motion as purely relative, like, standing on a train, where your speed depends on whether you compare it to the ground or the train itself.
Yeah, standard relativity.
Right. They propose a fundamental non-arbitrary background. It's almost like a cosmic zero point from which the electron gains its initial velocity. It's challenging the very idea that all inertial frames are equivalent, suggesting there's a true resting state for momentum to be imparted against.
Okay.
And this is critical because they propose that to conserve the total mass energy inventory of the universe, this frame cannot be relative or arbitrary. It ties into a much deeper view of the cosmos, actually.
So the truly surprising core concept that allows this reactionless nature is that the object of reaction isn't another physical mass or exhaust,
Right, no propellant.
but what they refer to as spacetime that propagates the photon. This is a truly mind-bending idea. It suggests that the force isn't pushing off another object in the traditional sense, but interacting directly with the very fabric of space and time itself.
Yeah, it's like sailing on the ocean. But the ocean itself is propelling you without needing a sail or oars, like you said.
That's a great analogy.
And if we connect this to the bigger picture, it fundamentally differentiates space drive from conventional propulsion methods. Jet engines, rockets, as we discussed, they rely on what's called reactive momentum transfer.
Throwing stuff out the back.
Basically, yeah, they literally expel mass, like exhaust gas, to generate thrust. This expulsion inherently means mass loss from the system, which is why rockets are so heavy with fuel.
Absolutely massive tanks.
And it's also incredibly power inefficient in terms of converting energy into usable thrust. Most of the energy goes into heating and accelerating the exhaust, not directly propelling the craft itself.
Which is why you need those massive fuel tanks for rockets that often make up the vast majority of the vehicle's weight.
Exactly.
The source emphasizes the huge advantages of space drive. It requires no mass loss for propulsion. Think about that. No need to carry tons and tons of fuel.
Game changer right there.
And it boasts a significantly higher power efficiency, potentially 70% or more, which they say can be further boosted in a closed system through energy recovery. This isn't just a slight improvement, it's a paradigm shift in how we move.
Completely.
The foundational mechanism for this is a directional increase in the kinetic energy of a free electron upon absorbing a photon, like a microwave photon. This results in what they call a reactionless force, or lift.
That's right. It's about imparting kinetic energy to electrons in a specific direction without the apparent recoil you'd expect based on, well, everything we thought we knew. The key is how this directional flow is achieved and then harnessed.
Okay, so if the theory is that an electron absorbs a photon and gets this unrecoiled kick, how does this space drive actually create a directional force from that? It all starts with that photon-electron interaction. Can you walk us through the precise dance between them?
Sure. The process is quite specific. An incident photon, let's say a microwave photon, interacts with a free electron. And crucially, it increases the kinetic energy of that electron in its initial direction of motion.
Ah, okay. So direction matters from the start.
Absolutely. So, if an electron is already moving upwards, absorbing a photon makes it move more upwards, like a tiny, perfectly aimed boost.
But then there's that quantum mechanical twist, isn't there? You mentioned linear momentum isn't obeyed in the traditional sense. That's the huge claim. For listeners, what's the typical expectation here, and how does this paper argue for such a radical departure?
Indeed, this is where it gets truly fascinating and controversial for conventional physics. Normally, in any interaction, we expect momentum to be conserved. Total momentum in equals total momentum out.
Right.
If a photon hits an electron, both should recoil in some way to conserve the total momentum of the system. But this theory states that while conservation of photon energy, represented as ong, and angular momentum, is obeyed.
Okay, so some things are conserved.
Right, those are fine. But linear momentum is not obeyed in the conventional particle-to-particle sense. Instead, the electron gains kinetic energy equal to half the photon energy.
Only half. Where does the rest go?
Well, the argument is that the other half of the momentum is effectively transferred to the absolute space inertial frame, or space-time itself.
Yeah.
So normally, if you throw a baseball, your body moves back a bit, equal and opposite reaction.
Yeah.
They are saying it's like throwing a baseball, and your arm doesn't recoil, or maybe even gets pushed forward. It suggests a transfer of energy and momentum directly with space-time itself, without needing a physical object to push against in the traditional sense.
Wow. That's a concept that really forces you to reconsider the fundamentals. So if the electrons are absorbing photons and gaining kinetic energy in a particular direction, how do you get that into a bulk flow, especially in something like a plasma?
Yeah, that's a good point.
Because as the paper points out, typically in microwave plasmas, electron motion is pretty random, right? It just leads to heating with no net directional flow.
Exactly. This raises an important question, because random motion would just create heat, not thrust. To overcome this, space drive requires establishing a directional electron flow bias. You need a way to nudge a sufficient number of electrons to start moving in a preferred direction to get a collective movement going.
Like giving them a little hint.
Sort of, yeah.
Yeah.
You need an initial asymmetry.
And once you have that slight bias, how do you amplify it? It sounds like there's a positive feedback loop involved somewhere.
Precisely. It's described as a self-amplifying process. A slight initial bias in the plasma, perhaps from the initial gas flow maybe, leads to a small excess of electrons that happen to have their maximum velocity projection in a selected direction, let's say vertical.
Okay.
These biased electrons then preferentially absorb microwave photons because of that directional interaction we talked about. This absorption further increases their directionality, making them move even more vertically.
Ah, so the ones already going the right way get boosted more.
Exactly. It's a rapid, self-organizing process that quickly funnels the plasma electrons into a full directed electron flow, like a snowball effect.
So once the electrons are moving directionally, how does that translate into a force that can actually push something? We're talking about tiny electrons here. They're not exactly going to push a spacecraft on their own, are they?
Right, good point. They're way too light. This is where ion dragging comes into play.
Ion dragging, okay.
Once the electrons are directionally accelerated by the space dries effect, their collective movement, their negative charge, drags the much heavier positive ions along with them through electrostatic attraction.
Like attracts opposite.
Pretty much.
Yeah.
And then these ions, now moving directionally, in turn, accelerate the collisionally coupled neutral plasma gas. They bump into the neutral atoms and get them moving too.
So it's a chain reaction. Electrons pull ions, ions push neutrals.
You got it. So you end up with a directed macroscopic plasma flow, not just a random heating effect. It's like a rapidly flowing river where the fast-moving water drags along the heavier sediment and even branches.
And that directional kinetic energy from the plasma flow is what's then manifested as a measurable lift force when it hits something.
Exactly. To convert this directional flow into a measurable force, you need what they call a transducer. This could be something sophisticated like a plasma flow arresting magnetohydrodynamic generator.
Whoa, MHD generator. That sounds complex.
It is. It basically turns the energy of a moving gas directly into electricity without moving parts. Or it could simply be a physical barrier, like a plate.
Ah, much simpler.
Yeah. When the directed plasma flow impacts this barrier, it transfers its kinetic energy to the object to be propelled, creating the measurable lift. It just slams into it directionally.
All right, so we have this wild theory, this proposed mechanism for how it might work. But the real proof is in the pudding, or in this case, the lab. Let's talk about the experiments. The paper starts by revisiting some previous work, right? Setting the stage.
Yes, and it's a crucial starting point to understand why their work is potentially so significant. Researchers at Wuhan University, led by Ye Ada, conducted experiments with atmospheric pressure microwave plasma torches, trying to create lift.
Okay, so others saw lift too.
They did observe lift, yes. But their initial interpretation was that it was due to conventional thermal heating of air and static pressure from the flowing gas. Hot air rising, gas pushing things.
A standard explanation. Seems reasonable.
A very conventional explanation, yeah, aligning with typical fluid dynamics, the kind of forces we understand in, say, rocket science or jet engines.
But the reactionless propulsion paper offers a critical reanalysis of that work, right? They argue that Ye-L's conclusion about net propulsion force was actually incorrect. This is where they begin to lay the groundwork for their own, more radical explanation.
That's correct. The study meticulously explains that when you apply proper nozzle physics, as later argues by other researchers like Wright et al., at UCLA, any actual thrust from the gases escaping through the small aperture in Ye's setup would have been orders of magnitude less than the lift they observed.
Orders of magnitude, so way smaller.
Way smaller. They found that the upward force of the pressurized gas on the ball they used and the ball's weight were essentially equal and opposite. And the pressure forces on the plasma tube also balanced out.
So net zero force from conventional effects.
Pretty much. This means there was no net propulsion force on the system itself when analyzed correctly using standard physics. This reanalysis is pivotal, as it strongly suggests that the observed lift was not due to conventional thermal expansion or reactive thrust.
Okay.
It systematically rules out what we thought we knew, setting the stage for an unconventional force, like space drive, to be at play.
Okay, so with that precedent setting the stage, let's dive into Experiment Series 1, the flattened waveguide plasma jet studies. This is where Mills's team started their own direct observations, trying to replicate and then understand this strange lift. What did their apparatus look like, and how did they set up these initial tests?
Right. They used a pretty powerful Aztecs microwave system. It included a 1,500-watt microwave power generator, a magnetron that's the bit that actually generates the microwaves.
Like in a microwave oven.
Exactly, but more powerful. And an isolator, a circulator, and a 3-stub tuner to control the microwaves.
Ah.
But the core component for their direct observations was a custom flattened copper waveguide.
Okay, what's that?
Think of it as a specialized elongated metal tunnel about half a meter long, specifically designed to direct microwaves. It had specific dimensions, flattening to a narrower section where they inserted a 23-millimeter outside diameter quartz plasma tube through circular holes.
Got it. A channel for the microwaves with a tube running through it.
Precisely. And plasma ignition was done using a Tesla coil, which generates a high-voltage spark to kickstart the plasma inside the tube.
And for gas flow, they initially had some issues with consistency, didn't they? Getting precise control sounds crucial for these kinds of measurements.
They did. Initially, they used something called an Alicat constant pressure flow controller. It's fast-acting, which sounds good, but it proved problematic here.
How so?
When they added weight to measure the lift, the rapid response of the controller caused these tiny, transient interruptions in gas flow, enough to extinguish the plasma.
Ah, not good for experiments.
Not at all. They quickly learned they needed something more stable, so they replaced it with a much slower, more consistent VWR scientific gas pressure regulator connected to an air tank. This provided a far more consistent, steady gas flow, which was crucial for getting reliable experimental conditions.
So with this refined setup, what were their initial lift measurements? Were they able to replicate those intriguing numbers from Yiel's earlier work?
They absolutely did. They performed baseline measurements using a 75.5 millimeter outside diameter steel hollow ball placed on a sensitive scale. Without any microwave power, just gas flow, they measured a baseline lift of 0.3 pounds, which is about 0.136 kilograms.
Okay.
But then, when they applied 400 watts of microwave power, the lift increased to 0.5 pounds, or about 0.227 kilograms.
So an increase.
Right. This resulted in a net lift over the baseline of 0.2 pounds, or 0.091 kilograms. And what's really significant is that this figure directly matched the net lift reported by Ye et al. At that same 400 W power level.
Okay, so replication confirmed. That's important.
Very important. It proved they could reproduce the initial phenomenon, which was the necessary first step before digging deeper into why it was happening.
But then they observed something truly striking, something that immediately screams impossible under conventional understanding. The plasma jets extending far outside the microwave power region. This is where it starts to get really wild, isn't it?
Oh yeah, this is where the conventional explanations truly fall apart, and the need for something like space drive becomes much more apparent.
So what did they see?
They observed plasma jets extending up to 438 millimeter, that's almost half a meter outside the waveguide where the microwaves were being applied. And previous studies, like Ye et al., had reported jets up to 600 millimeters, and Lines et al. Up to 564 millimeter.
Half a meter long, just hanging in the air.
Essentially, yeah. Think about it like this. Imagine a candle flame staying lit and perfectly upright, perfectly shaped, maybe 100 feet away from the candle itself, with no visible wick or fuel line connecting them.
Okay, that's impossible.
That's how impossible these continuously maintained plasma columns seem under conventional physics. It truly forces us to ask, what else could be powering and confining them?
So why is it so impossible? What specific physics does it violate? Break that down for us.
Okay, there are multiple really compelling reasons why this shouldn't happen according to standard models. First, the microwave frequency they used, 2.45 gigahertz, is over 2,000 times below the typical plasma cutoff frequency for atmospheric pressure plasmas.
What does that mean, cutoff frequency?
It means the microwaves simply shouldn't be able to propagate through the dense plasma. It's too dense. It should reflect or absorb them right away. This rules out a common explanation called a surface wave, where microwaves supposedly ride along the plasma surface.
So no surfing microwaves. Got it.
Right. Second, even if such waves could theoretically form, they're known to be highly prone to plasma instabilities. They just wouldn't be sustainable in such a long, freestanding jet. They'd break up.
Okay, so plasma instability is another issue. What else?
Third, the quartz tube walls are non-conductive. They're insulators. So they can't support a traveling transverse wave, which is another proposed conventional way for energy to travel down the tube.
Tube walls don't help.
Nope. Fourth, typically the electron temperature and density are highest in the center of this kind of plasma, not at the perimeter walls. This indicates it's not being driven from the outside along the surface. The action is in the core.
Center-driven, not surface-driven.
Okay. Fifth, From a simple power conservation perspective, diverting enough microwave power outside the waveguide to maintain such a long external jet would cause the plasma inside the resonator itself to extinguish due to the field loss. But that wasn't observed. The resonator plasma remains stable.
Ah, so you can't power both strongly.
Not like that, no. The energy has to come from somewhere, and there wasn't enough leakage indicated.
So it's not some kind of external energy source leaking out efficiently. What about the plasma itself? Does it just kind of flow out like water from a hose carrying its energy with it?
Well, not in the way you might think conventionally. Sixth, there's no plasma dielectric interface for a surface wave to propagate along anyway, because intentionally, they create a gas vortex.
A vortex? Why?
To prevent the superhot plasma from contacting the quartz tube walls directly. If it touched, the intense recombination heating would melt the quartz pretty quickly.
Ah, clever. Protect the equipment.
Exactly. But this vortex means no surface for a wave to ride. And here's another critical point. The plasma is observed continuously outside the dielectric tube as a free plasma jet, with no discontinuity at the exit of the resonator.
Seamless transition.
Yes, which implies the resonator is the continuous power source, somehow, even if no power is measurable outside, which brings us to the next big problem.
And the power leakage. You'd think if something was being powered from the inside, there'd be some measurable microwave leakage you could detect outside.
Well, you'd absolutely expect that, but it's not what they found. Seventh, the aperture size for the tube is typically around 2.54 centimeters, but for significant microwave leakage to sustain a distant plasma, you'd need an aperture size closer to the wavelength of the microwaves, which is 12.24 centimeters for 2.45 gigahertz.
So the hole's way too small for microwaves to leak out efficiently.
Far too small. And crucially, multiple studies, including this one and others by researchers like and Lyons et al., reported no detectable microwave power emission from the jet anywhere outside the small fringe field zone right near the waveguide opening.
No microwaves detected outside. Wow.
This means no measurable external microwave energy is sustaining these jets for the observed distances. It's like the power is invisible.
And then there's the plasma recombination lifetime.
Yeah.
You said earlier this is perhaps the most compelling piece of evidence against conventional explanations. This detail really stood out to me too.
Absolutely. This is arguably the crucial nail in the coffin for traditional understanding. Eighth, atmospheric pressure air plasma, once its power source is removed, recombines and basically disappears in less than 10 microseconds.
10 millionths of a second. That's incredibly fast.
Vanishingly fast. Imagine a spark from a lighter. How long does that superheated air stay glowing? Blink and you miss it.
Right.
Yet the observed jet duration, for example, the 1.12 seconds required for the plasma to propagate 0.564 meters in the Lyons Gamma experiment, well, that's an astounding 114,000 times greater than what's possible without continuous power and confinement.
114,000 times longer. That's not even cool.
Not even in the same ballpark. This observation alone strongly indicates that some unknown continuous force is sustaining and confining the plasma far beyond its natural recombination lifetime. It's like watching that candle flame stay lit and perfectly shaped hundreds of feet away, even after the candle itself has gone out.
So what is the explanation then, if not all of these conventional physics principles? What does the paper conclude is happening?
The paper concludes that these observations strongly indicate space drive is the mechanism for both the plasma confinement and the directional pressure causing the jet.
Both things, confinement and propulsion.
Yes. And the jet height showed a clear linear proportionality to the microwave power applied and an inverse proportionality to the gas flow rate. This behavior is completely consistent with the predictions derived from the space drive theory.
And not consistent with the other explanations.
No. This observed scaling simply cannot be explained by surface wave propagation, thermal effects, or any other known conventional plasma physics. It points strongly towards a fundamentally different interaction.
And there's a particularly enlightening demonstration from a video by Lyons et al. That confirms this. Isn't there something you can actually see?
Yes. This video is quite illustrative, really drives the point home. It shows the plasma actually disconnecting from the microwave cavity entirely.
Disconnecting.
Yes, physically separating.
Yeah.
And existing only vertically outside the cavity while the cavity itself goes dark. No glow inside.
Whoa.
This is perfectly consistent with what they call a dark current. Electrons and ions moving due to space drive, but not emitting light until they recombine sustained by space drive, rather than any external microwave power leaking out. It vividly illustrates that thermal or airflow confinement is impossible for this detached plasma.
He's an active force?
Exactly. An external continuous force, namely space drive, is required to maintain such a distant and confined plasma. The plasma cannot be simply confined by temperature or airflow. It requires interaction with external forces like magnetic or electric fields, or in this case, they argue space drive provides that force.
Okay, that was Experiment Series 1, focusing on those really mysterious plasma jets. Now, let's move to Series 2, the microwave oven cavity experiments. This shifted focus to directly measuring pulsed space drive lift. Why did they shift to this setup? What was the motivation behind using something as seemingly mundane as a standard microwave oven?
Yeah, it seems funny, right? It's
Yeah.
$60 microwave.
Right.
But the motivation for this new setup was actually brilliant in its simplicity and cost-effectiveness. They wanted to better achieve what they called free space photons, and crucially, eliminate the thermal and gas flow pressure components that had complicated the measurements in the previous waveguide experiments.
Get rid of the confounding factors.
Precisely. A commercial microwave oven, costing around $60, was ideal because its cavity dimensions, roughly 2 wavelengths of the microwaves in all directions, allow for the propagation and multi-reflection of free photons. This helps ensure that the microwaves were incident on gas molecules or atoms at the initiation point of the space drive event, simulating free space better. This larger, more open environment also allowed for precise pulsed measurements, which largely removed any confounding continuous thermal effects, allowing them to better isolate and measure the space drive force itself.
So they literally used a standard microwave oven, maybe like the one in your kitchen. That's quite a leap from scientific lab equipment.
Exactly. A standard commercial microwave oven measuring about 25.2 centimeters high, 35.3 centimeters wide, and 36.6 centimeters deep. Nothing too fancy there. The ignition method, though, was clever and precise.
How did they start the plasma in there?
They used an arc generated on serrated aluminum foil, which was placed on a mica sheet. A mica is a good insulator. The arc creates the initial free electrons and plasma spark needed to get things going.
Like a tiny lightning strike inside the oven.
Kind of, yeah.
Yeah.
And they meticulously mapped the microwave field intensity inside the oven beforehand to find the best spots for consistent arc generation. They wanted to make sure they initiated the plasma reliably in the same way every time.
And what kind of vessel did they use for containing the plasma within the oven? Couldn't just let it loose in there.
No, definitely not. They used a right cylindrical quartz. Beaker quartz is good because it's transparent to microwaves and can handle high temperatures. It was a pretty robust container. 152.4 millimeter internal diameter, 152.5 millimeter high, with a sturdy 4 millimeter wall thickness. And importantly, it had a carefully lapped flat rim.
Why flat?
To ensure a really tight seal when they put a cover on it. This vessel was then used in both inverted and non-inverted orientations to study the plasma's behavior and the resulting forces under different conditions.
This leads us to another truly stunning observation they reported. The plasma confinement itself. You mentioned it was tightly confined as a layer at the top for very long periods.
Yeah.
How did the plasma behave once initiated in this closed vessel, and why is this so significant?
This was a really key finding, perhaps even more visually striking than the jets. Once initiated by the spark, the plasma didn't just randomly dissipate or fill the beaker. Instead, it traveled ballistically, meaning it moved very directly and rapidly, like a projectile. Straight up to the top of the closed quartz vessel. And then, astonishingly, it was observed to be tightly confined as a layer right against the top surface for very long periods of time, sometimes for more than minutes. More than minutes, confined, just sitting there, glowing, pressed against the top lid. It wasn't just briefly held there, it was stable, sustained.
And this confinement occurred in the absence of any other external known confinement force, such as one provided by a magnetic field. That's a huge claim for something like plasma, which is notoriously difficult to contain, right? Needs huge magnets, usually.
It absolutely is.
Yeah.
Plasma, being this super hot ionized gas, typically wants to expand rapidly unless it's confined by extremely powerful magnetic fields, like in fusion reactors or some other external pressure. This observation is fundamental because it challenges the known methods of plasma confinement.
So how do they explain it?
The paper reiterates that conventional thermal or airflow mechanisms simply cannot achieve this kind of sustained, tight confinement. Instead, space drive is proposed as the net vertical force acting on the electrons and the ions they drag along.
The same mechanism as the jets, but now for confinement.
Exactly. This upward space drive force balances what they call a downward neutral gas recombination pressure gradient. Essentially, that's a downward push from the neutral gas trying to recombine where it's cooler, away from the hot plasma layer.
So it's a balance of forces, space stride pushing up, recombination pressure pushing down.
Precisely. This balance creates a stable, confined plasma layer, and it was evident visually by a distinct dark space along the side walls of the beaker.
A dark space.
Yeah, where the plasma recombines into neutral gas, which then flows away from the walls, leaving a gap. The dark current of accelerated electrons and ions, which aren't emitting much light or heat yet, travels upward, hits the boundary, and then the recombination releases light and heat, keeping the plasma visibly confined against that top boundary.
That's an incredible picture. So they saw this amazing confinement. How did they actually quantify the lift force produced by this space drive? How did they measure something so precise?
Right, seeing is one thing, measuring is another. For measuring the maximum lift, they set up the quartz vessel in its non-inverted orientation, so right side up,
Huh.
and carefully closed it with a quartz cover plate.
Okay, sealed container.
Then, they incrementally added weights on top of the cover. They used stacked quartz plates and even standard cement bricks.
Cement bricks.
Seriously,
Yep.
to get enough mass. These weights were loaded onto a special bearing system. This allowed the weights to self-center freely and apply force evenly downwards without tilting or friction interfering.
Okay, so how did they know when it actually lifted? Must be subtle.
Very subtle. The moment of lift, where the space drive force just overcomes the weight, is hard to pinpoint. So they used a multifaceted approach for detection. High-speed video to visually confirm the slight separation, high-speed audio to listen for the precise moment the rattling noise of the weights stopped.
Because it's floating.
Exactly. And a sensitive vibration detector placed on the weights to fine-tune the exact endpoint of lift. And the weights themselves were measured with impressive 0.1 gram accuracy, ensuring really precise data on how much mass was being lifted.
And how much microwave power were they putting into the system to achieve these lifts? Must have been a lot to lift bricks.
That's the kicker. The microwave power actually applied to the plasma was precisely determined through careful water heating experiments conducted within the oven cavity itself, basically seeing how fast it heated a known amount of water. And it was consistently found to be only 330 watts.
330 watts, that's less than many kitchen microwaves on full power.
Exactly. It's remarkably low power for the kind of forces they were measuring. This precise power measurement allowed for accurate calculation of the force generated per unit of power, which is crucial for understanding its potential efficiency.
Okay, so low power, high lift, amazing confinement. Beyond just measuring the lift, they also characterize the plasma itself, right? To understand the science behind the force and confirm the conditions.
Absolutely. That's critical for linking the observed force back to the theory. You need to know what's going on inside that glowing gas.
What methods did they use for this plasma characterization? How do you measure stuff inside plasma?
They used a technique called optical emission spectroscopy, or OES. They used a MITEC system spectrometer. Think of OES as analyzing the specific light fingerprint that the plasma emits. Different elements and conditions produce different colors and spectral lines.
Reading the light signature.
Exactly. By studying this light in detail, they could measure key plasma parameters. For instance, the electron density, usually written as Ness, how many free electrons are packed in there, was determined by analyzing something called stark broadening of the H spectral line.
Stark broadening.
Yeah, it's basically how much an electric field like the one from nearby ions and electrons in the plasma smudges or widens a specific spectral line of hydrogen. HO is at 486.1 nanometers. It's a very sensitive technique, chosen for its strong broadening effect and weak self-absorption, making it reliable.
Okay, so that gives electron density. What about temperature?
Electron temperature, Te, was then derived from something called a Boltzmann plot, which looks at the relative intensities of different spectral lines from the same element. This assumes partial local thermal equilibrium, or PLTE, which is often a reasonable assumption in these kinds of plasmas. It allowed them to get a very accurate picture of the plasma's state, how hot the electrons were.
And they tested different plasma gases. I imagine the type of gas would play a significant role in how the space drive effect manifests, right? Different atoms, different properties.
Yes, absolutely. They systematically tested 4 different conditions. Standard ambient air, pure nitrogen N2, pure argon, RR, and a carefully prepared mixture of argon plus 5% hydrogen, R plus 5% H2.
Why those specific gases?
They offer different atomic masses, ionization energies, and chemical properties, allowing for a systematic study of how these factors influence the space drive effect. The preparation methods were meticulous to ensure controlled conditions.
How so?
Well, they used ambient air for the air experiments, obviously. For nitrogen and argon, They perform 10 volume exchange purges, basically flushing the container 10 times with the pure gas to get rid of any air. And critically, the argon plus 5% hydrogen experiments were conducted inside a sealed two-man glove box.
A glove box, like for handling sensitive materials.
Exactly. This allowed them to fill the beaker with a precise gas mixture and match the internal pressure exactly to the ambient atmospheric pressure outside the box before sealing it. This level of control ensured that the results from each gas type were directly comparable, without pressure differences messing things up.
Okay, meticulous setup. So let's get to the brass tacks.
Hmm.
What were the key results from their measurements, especially from Table 2 in the paper? What did they find about the lift values for each gas? And importantly, how did these observed values compare to their theoretical calculations based on the space drive model?
Right, this is where it gets really interesting. The results were quite compelling and provided strong quantitative support for their theory. They showed a direct and remarkably close comparison between the calculated lift values based on the measured plasma properties and the space drive equations, and the actual observed lift values for each gas type.
Okay, give us the numbers.
For atmospheric air, they observed 12.2 kilograms of lift with a calculated value of 14.6 kilograms. Pretty close.
12 kilograms from 330 watts in air. That's already impressive.
It is. For pure nitrogen, they observed 15.5 kilograms versus a calculated 22.3 kilograms, still in the same ballpark. For pure argon, they got 21.4 kilograms observed against 22.7 kilograms, calculated. That's a very close agreement.
Wow, argon worked even better.
It did. But the real star was the argon plus 5% hydrogen mixture. For that, they observed an incredible 47.0 kilograms of lift compared to a calculated 63.7 kilograms.
47 kilograms, that's over 100 pounds. Lifted by 330 watts of microwaves in a beaker.
Exactly. The close agreement between the observed and calculated values across these different gases, especially for argon and air, is very significant. The paper states it indicates that space drive has the effect of converting the omnidirectional plasma pressure into directional pressure and force. It suggests the model is correctly predicting the outcome.
That's a lot of weight for only 330 watts of microwave power. And speaking of that argon plus 5% hydrogen mixture, it really stands out. A dramatic increase in performance, reaching 47 kilograms of lift. Why is adding just 5% hydrogen so incredibly effective in this mix? What makes it such a powerful addition?
Hydrogen truly becomes a game changer here. It brings several distinct advantages to the plasma dynamics that seem to supercharge the space drive effect.
Like what?
Firstly, it significantly increases ionization within the plasma, meaning more free electrons are generated for the same power input. It also enhances thermal diffusion, ion mobility, and thermal conductivity, which all improve the overall gas dynamics and energy transfer within the plasma.
So it just makes the plasma lighter, more active.
Yeah. In many ways, yes. But a key specific factor they highlight is the formation of the H3 plus ion.
H3 plus three hydrogens.
Yep, a molecular ion. Its concentration increases linearly with pressure, apparently. And crucially, it's significantly lighter than other common ions in these plasmas. For example, H3 plus has a mass-to-charge ratio of about 3 mu per charge. Compare that to R plus at around 40, or N2 plus at 28.
Much, much lighter.
Much lighter. And this makes H3 plus much easier to drag and rapidly accelerate by the microwave-accelerated electrons. Lighter ions have less inertia, right? They respond much more readily to the forces from the electrons trying to pull them along.
So it's easier to get them moving in the right direction, creating that powerful directional flow needed for the lift. Makes sense.
Exactly. More efficient momentum transfer from electrons to ions.
But what about ion lifetimes? Don't some of these lighter ions have shorter lifetimes, which might seem counterproductive if they disappear too quickly?
That's a valid point, and the paper touches on it. While H3 plus might have a shorter lifetime than, say, R plus or, the genius of the mixture is that it seems to cleverly exploit the longer R plus lifetime. Argon is still 95% of the mix, while still leveraging the powerful acceleration benefits of the lighter hydrogen ions.
Best of both worlds.
Possibly. Additionally, hydrogen has a lower ionization energy, only 13.6 electron volts compared to argon's 15.8 eV. This makes it inherently easier to knock an electron off and produce those critical free electrons in the first place. Hydrogen molecules are also easily excited and ionized through stepwise processes, further contributing to the generation of free electrons and ions.
Easier to make the plasma, easier to move the ions.
That seems to be the idea. And for practical considerations, the fact that R plus 5% H2 is a commercially available welding gas, sometimes known as ArHY5.
Oh, you can just buy it.
Yeah, it indicates its practicality and relative safety. Importantly, this mixture doesn't detonate when mixed with air, which is a major safety benefit for experiments and potential applications compared to using pure hydrogen.
Okay, this is all incredibly fascinating, mind-bending, really. But for many people listening, the biggest question mark will still be, is this just some really efficient, maybe subtle form of thermal propulsion? It seems intuitive that heating a gas like that can produce force.
Right, the hot air balloon effect, scaled up.
Exactly. But the paper provides what they claim is definitive evidence that space drive is not thermal. This is such a crucial distinction, and frankly, another one of those jaw-dropping claims. What's the proof they offer?
This is a critical point, and the paper addresses it head-on with several lines of pretty undeniable evidence if their measurements are correct. First, let's look at the power balance again.
Okay, where'd the energy go?
Of the 330 watts of microwave input power that was absorbed by the plasma, they measured a remarkable 322 watts being emitted as light from recombination.
322 out of 330. That's almost all of it.
Almost all of it, over 97%. This means essentially all the microwave power absorbed is emitted as light during the ion-electron recombination phase, not significantly converted into bulk gas heating. This immediately and profoundly challenges any thermal explanation. If the energy isn't going into heat, it can't be a thermal engine driving the lift.
So almost all the absorbed power comes out as light, not heat.
Oh.
What about direct temperature measurements? You'd expect something generating over 100 pounds of lift to be getting incredibly hot if it were a thermal effect, right? The beaker should be melting.
Exactly. And their measurements showed the opposite. Using thermocouple's very precise temperature sensors, they found no thermocouple measured temperature rise
Yes.
at an accuracy of 0.1 degrees C on the atmospheric air plasma experiment that was observed to lift over 12 kilograms.
No temperature rise at all. That's astonishing.
Within their measurement accuracy, no significant rise. The calculated temperature rise from any hypothetical residual thermal input, assuming all the unaccounted power went to heat, was negligible anyway, around 0.03 degrees C. This is an astounding finding. It effectively says, we moved 12 kilograms and the system didn't even get measurably warm.
And what about the ignition source, the little spark from the aluminum foil? Could that contribute to heating? A little combustion could create some heat, right? Maybe that's the trick.
They checked that too, very rigorously. The aluminum foil combustion, which was only used for the initial spark to start things, was found to be negligible in terms of energy contribution. They measured the foil before and after. No detectable weight change was observed, meaning no significant amount burned.
Okay.
And the calculated temperature rise from its potential complete combustion was only a minuscule 0.045 degrees C. Furthermore, the pristine reflective metallic surface of the foil after repeated experiments confirmed no significant chemical reaction or heat contribution from the ignition source. It was just a trigger.
So the spark didn't do it. What else? You mentioned a sonic boom earlier. That doesn't sound very thermal.
No, it doesn't. That's another key piece of evidence pointing away from thermal effects. The plasma sound speed was calculated based on the measured electron temperature, and it was consistently found to be supersonic, faster than the speed of sound in the surrounding gas.
Supersonic plasma.
Yeah, and the paper reports observing a distinct sonic boom sound at the precise moment of maximum lift during the experiments. This indicates the production of a shock wave.
Like a tiny sonic boom from the plasma hitting the lid?
Exactly.
Yeah.
This is inherently a kinetic effect, driven by the rapid directional motion and impact of the plasma. It's about momentum transfer, not a thermal effect, which would manifest as a slower, more diffuse expansion or pressure rise. Taken together, these lines of evidence, the power balance showing light emission dominates, the lack of temperature rise, the negligible ignition energy, and the supersonic shock wave, they all strongly demonstrate that space drive, as observed here, is a separate force and not a thermodynamic heat engine effect. It's fundamentally different from a jet engine or rocket relying on heat.
This is incredible, truly paradigm-challenging stuff. If these experiments hold up under further scrutiny and are reproducible by others, and the paper certainly details a rigorous methodology, what does this mean for the future? How scalable is this technology, and what are its commercialization prospects? We're talking about a potential revolution here.
The implications are, well, potentially enormous, staggering even, for everything from earthbound transport to interplanetary travel. Let's start with the prototype's performance in that microwave oven.
Yeah, the 330 watts lifting 47 kilograms.
Right. That translates to a lift capability of about 3 watts per pound of lift generated. Now, to put that in perspective, let's compare it to something cutting-edge we know, like SpaceX's Starship Raptor engines. Their thrust-to-power ratio implies something like 655,000 watts per pound of engine weight, though comparing lift power to engine weight power isn't direct. But the point is, The space drive's efficiency in converting input power to lift force looks very favorable, especially considering this is an early prototype.
Okay, so it's efficient in principle.
Very. And the projected efficiency, especially if you incorporate energy recovery using that MHD channel idea we mentioned.
Right, getting electricity back from the recombining plasma.
Exactly. They projected over 90% electrical power efficiency to propulsion can be achieved.
Over 90% efficiency. That's almost unheard of in propulsion systems. Most lose tons of energy as waste heat.
It's exceptionally high, which leads to the question of scaling it up to megawatt levels enough for real-world applications. That's where the rubber meets the road, so to speak.
So how do you get megawatts of microwave power, and how much would it cost? That sounds expensive.
Well, there are clear and surprisingly practical pathways outlined. For very high power sources, things called compact gyrotrons operating at megawatt scale already exist. They're used in demanding applications like heating plasmas for fusion research.
Okay, so the tech exists. Expensive.
Currently, maybe around $1 per watt for microwave power from those specialized devices. So a megawatt might be $1 million. But there's a much more affordable route they suggest.
What's that?
Simply ganging commercial microwave oven magnetrons. Remember, each magnetron is roughly 1,000 watts and costs about $25.
Just string 1,000 of them together.
Essentially, yes. Design a system to combine their power. This means 1 megawatt of microwave power, which is enough to power a small town, or potentially a massive propulsion system, could theoretically be generated for as little as $25,000 using off-the-shelf components.
$25,000 for a megawatt microwave source. That makes scaling seem incredibly cost-effective, not just efficient.
Exactly. It potentially removes a major economic barrier to developing high-power systems.
So we're talking about not just incredibly efficient, but also potentially very affordable power at large scales. What does that translate to for the actual thrust potential? Could this realistically power actual vehicles? Or are we still talking about lab experiments lifting bricks?
Oh, absolutely. The potential is for powering vehicles on an unprecedented scale. The paper highlights the significant scalability of space drive. Its power, they theorize, increases with electron density. And electron density has been shown in other plasma research to increase with gas pressure, potentially to very high levels, like over 34 atmospheres.
Higher pressure, more density, more thrust.
That's the idea. And to give you an illustrative calculation from the paper, if the microwave power is scaled up to 1 megawatt and the geometric parameters of the device are optimized, meaning the design is perfectly suited for maximizing the effect they calculate, the space drive thrust could easily increase to over 1 million pounds.
1 million pounds of thrust from 1 megawatt.
That's the projection based on their model and scaling laws. 1 million pounds.
Let's contextualize that for our listeners again. A modern fighter jet, like the F-35, has a maximum thrust of around 40,000 pounds from its engine. So this hypothetical 1 million W space drive could generate 25 times that amount. That's simply mind-boggling for a single propulsion system.
Precisely. It's vastly superior to current jet engine technology in terms of potential thrust density. And the consequences for vehicle design are profound. A space drive craft is anticipated to be much smaller and lighter than, say, a 70,000-pound F-35.
Why smaller and lighter?
Because you're no longer constrained by the need for massive heavy jet engines, huge internal fuel tanks, complex air intakes, or even wings designed for aerodynamic lift in the same way. You don't need to carry your reaction mass. It fundamentally changes the design parameters for anything that moves.
And the vision for this technology goes even further, a closed system for indefinite thrust. What does that look like? That sounds almost like perpetual motion, which has always been the holy grail for engineers, right?
Yeah, it skirts close to that territory, doesn't it? The ultimate vision is indeed a system that could provide thrust indefinitely, potentially orders of magnitude more powerful than current systems, and remarkably, as a truly closed loop.
How would that work?
The paper mentions another technology from the same company, the sun cell, as a potential compact, high-power onboard energy source, and the fuel source for the plasma, just water, serving as the source of hydrogen and oxygen.
Water as fuel.
Yes. The full cycle would work something like this. The onboard power source generates microwaves. Space drive uses these microwaves to create that dark current of accelerated electrons and the ions they drag. Remember, minimal light and heat emission at this stage.
Okay.
When this directed current attacks a physical boundary, maybe the backplate of the engine, the ions and electrons recombine. This recombination releases their ionization energy as radiation and heat.
Right, like we saw in the beaker experiment.
Exactly. But instead of wasting that energy, it can then be recovered as electricity using an MHD channel integrated into the boundary surface.
Ah, the energy recovery loop.
Yes. This MHD channel not only generates electricity to potentially feed back into the system, but it also helps to break the plasma and efficiently transfer the space drive kinetic energy to the object to be propelled. The resulting neutral gas, just hydrogen and oxygen again, if you started with water, can then be cooled and recirculated back into the plasma generation chamber.
Making it a completely closed, self-sustaining propulsion system. Wow.
It's a complete energy and propulsion cycle, needing only an initial energy input and water as the working fluid, theoretically.
That's astonishing. A truly closed-loop system that needs no external fuel beyond water and electricity to run, almost like a perpetual motion machine in terms of continuous thrust capability. So beyond just propulsion itself, what are the broader applications of a technology like this? What else could we do with a force that seems to defy Newton's third law?
The implications are truly revolutionary, potentially reaching far beyond just simple movement. First, for travel, as we've touched on, we're talking about unconstrained mobility, transmedium, omnidirectional craft,
Transmedium, like air and water.
and space. Imagine vehicles that can seamlessly transition between oceans, skies, and even the vacuum of space without needing different propulsion systems or shapes for each environment. No more runways, no more specialized spacecraft needing huge rockets, no more separate submarines or airplanes. It could be one vehicle for every domain.
A true all-terrain vehicle, and the travel times would be radically transformed, wouldn't they? If you could maintain a comfortable, constant acceleration, like maybe 2 times the acceleration of gravity, 2g, what kind of speeds and times are we talking about?
The calculations presented are genuinely mind-boggling and completely redefine our concept of distance. With the constant 2g space drive thrust acceleration, which is well within human tolerance for sustained periods, unlike higher g's.
Right, comfortable acceleration.
Travel times would shrink dramatically. There are examples. Philadelphia to Tokyo in just 18 minutes.
18 minutes, that's less than my commute.
Right. Earth to the moon in a mere 1 hour and 45 minutes.
To the moon in under 2 hours.
Yeah. And perhaps most astonishingly, Earth to Mars in just 2 days.
2 days to Mars, instead of 6 to 9 months.
Exactly. This would completely redefine our relationship with distance, both on Earth and in our solar system. It makes interplanetary travel potentially almost as routine as intercontinental flights are today.
Wow. Okay, beyond propulsion itself, the paper mentions another significant application: plasma confinement. How could space drive impact that field, especially given the huge challenges we face in trying to harness fusion power?
That's another potentially huge area. Space drive's demonstrated ability to tightly confine plasma, as observed so clearly in those microwave oven experiments, could have profound implications for future energy generation. Plasma confinement is a fundamental, incredibly difficult challenge in fusion research.
Yeah, keeping that super hot plasma stable.
Right. It currently relies on massive, complex magnetic fields, like in tokamaks, or intense inertial confinement using lasers. If space drive can provide a new, perhaps more efficient or less energy-intensive method of plasma confinement without needing those giant magnets, well, it could be a massive game-changer for achieving sustainable fusion power. It might unlock an almost limitless clean energy source.
A whole new approach to fusion. And finally, they mentioned novel applications for force generation beyond just movement. What else could this fundamental ability to generate directed force mean for us?
Yes, the potential for generating controlled shock waves is another intriguing application mentioned in the material. By creating sufficiently high space drive, plasma temperatures, and electron densities, where the resulting directed plasma velocity exceeds the local speed of sound.
Like the sonic boom they heard.
Exactly. You could potentially induce incredibly powerful and precise shock waves on demand. This opens up possibilities for various applications that are yet to be fully explored, perhaps, in material science, like shock-hardening metals, medical applications like lithotripsy, but maybe more controlled, or even specialized manufacturing processes. It implies a whole new way to exert precise and powerful forces without complex mechanical means.
What an incredible deep dive this has been. We've truly traversed some mind-boggling territory today, from challenging Newton's third law and the very fabric of space-time to envisioning interplanetary travel in days. The implications of this space drive concept are just immense.
Indeed. We've looked at the astonishing experimental findings. Those plasma jets extending 114,000 times longer than conventionally possible, over 100 pounds of lift generated from just a few hundred watts in a microwave oven, and the crucial evidence suggesting this force is non-thermal and represents a fundamental departure from classical physics. It's certainly a testament to bold scientific inquiry pushing boundaries.
So, what does this all mean for us? We've unpacked the intricate details of the experiments, delved into the underlying theory that attempts to explain these extraordinary claims, and glimpsed the incredible potential for scaling and commercialization of this technology. Now, the final thought for you, our listener. What do you think unconstrained mobility, a craft that needs no fuel beyond water and electricity, moving seamlessly through air, sea, and space, could truly mean for humanity's future here on Earth and for our exploration of the vast universe?
Yeah, it's a question that really demands a rethinking of what's possible, doesn't it? Not just in physics, but in our societal structures, our economies, maybe even our place in the cosmos.
This deep dive has just scratched the surface of a concept that, if proven true and scalable, could literally transform our world in ways we can barely imagine today.
Absolutely. The implications of reactionless propulsion are truly immense and invite us all to keep exploring, keep questioning the frontiers of science and engineering.
That's it for this deep dive. Until next time, keep exploring and keep questioning.